A rectangle is inscribed in a semicircle of radius 10. Find a function that models the area A of the rectangle in terms of its height, h. Then use a graphing calculator to find the maximum possible area of the rectangle. So we know that a semicircle is half of a circle, and this is probably the best approximation of a semicircle that I can draw by hand. And we know that the radius is 10, so the diameter is going to be 20. I'm going to write in 20 now. And we are talking about a rectangle that is inscribed in the semicircle. So when we inscribe one shape into another, it means that effectively the shape is inside the other shape and it's touching in a way that it can't really get any larger. So, of course, we could have, let me draw an example of something that's not inscribed. Like this rectangle is not inscribed because we could make it wider and it would still fit inside. So this is what it looks like to have a rectangle inscribed in a semicircle, but there are lots of ways that we could do this. We could have one that's taller and skinnier. We could have one that's shorter and wider. So there's lots of different ones that we could have. And what we want to do, though, is model the area in terms of the height that we choose, h. Now, 20 represents the diameter of the circle, not the width of the rectangle. We know that the area of a rectangle is the base times the height, or the length times the width, whichever we want to use. And so we need to figure out the width or the base of this rectangle. Now what we can do is we can use the fact that we know the radius is 10, and if we draw in a line segment from the center of the circle that the semicircle is a part of up to the upper right-hand corner of the rectangle, that is a representation of the radius. So that has length 10. And so if we want to find this distance here, which represents half of the base, we can use this right triangle and the Pythagorean theorem to figure it out. I'm just going to call this distance d. I don't want to call it b for the base of the triangle because we're using b to refer to the base of the whole rectangle. So let's call that d, and then using the Pythagorean theorem, we've got d squared plus h squared equals 10 squared. And we can use this to solve for that d in terms of h and 10. Now, 10 squared is 100, so this becomes d squared plus h squared equals 100. And then to get the d squared alone, we can subtract h squared from both sides. This gives us d squared equals 100 minus h squared. And then to get the d alone, we take the square root of both sides. We don't need a plus or minus symbol because it's going to be a positive distance. And we get the square root of 100 minus h squared. Now that represents this distance here. The total base of the rectangle will be twice that. So when we write this area as a function of the height, the base is going to be 2 times that distance, the square root of 100 minus h squared, times the height, which is h. And it looks a little bit nicer if we bring that h out front with the 2. So we get 2 times the height times 100 minus h squared. And this is the area as a function of the height. Now, we were also asked to use a graphing calculator to find the maximum possible area of the rectangle. Now, this is a complicated function that we don't really know how to find the maximum of algebraically. We've only looked at quadratic functions and finding their maximum values. This is a more complicated function, so what we're going to need to do is we're going to need to use a graphing calculator to get a graph of this to get an idea of what the maximum will be. You can go to Desmos.com to do that. I've done it as well, and I'm going to share a screenshot so we can see what the maximum value is. This is a graph of the area of the rectangle as a function of the height. Now, one thing that I want to point out, this part of the graph doesn't actually make sense because we can't have the height less than 0. The height has to be between 0 and 10. It can't be more than 10 because the radius of the circle is 10. And if it was more than 10, it would be taller than the circle, and it wouldn't be inscribed. But this is a graph of the function, and in Desmos you can go in and see what the maximum value is. And the maximum area is going to be 100, and it's going to occur when x is approximately 7.071. So we have a maximum area of 100, and we weren't given any sort of units, so we're just going to say the maximum area is 100, and this occurs when the height is approximately equal to 7.071. Now, this 7.071 isn't just a random number, it happens to be 5 times the square root of 2. But that's not something that we are capable of figuring out with the tools that we have yet. So the best that we can do with our graphing calculator is figure out the maximum area and an approximate value for the height that corresponds with it. In general, if we don't have the algebraic tools to solve a problem, it might be possible to use a graphing calculator to get a graphical solution.